right, give it a second. Okay, thank you, everybody. Welcome to the Houston Java Users Group meeting, for April 22nd, for April 27th, 2022. My name is Jim Bethencourt. I lead the Houston Java Users Group, and Michael Slater is our esteemed presenter today. He'll be talking about AI and ML for Java developers, because yes, machine learning can indeed happen on the Java virtual machine, even though Python gets all the hype. So Michael, without further ado, take it away.
Thank you, Jim. And yes, we can do some AI on Java. I will build a TensorFlow model at the end of this talk in Kotlin, actually, which means you can, of course, do it in Java. But, you know, I've moved on to better syntactical languages on the JVM myself, personally. There we go. My arrow keys. There we go. Now they're working. A little bit about me. I'm technical director here at Improving. What that means, kind of a fancy title, but all it means is I meet with businesses doing cool things and I discuss their problems with them and see if Improving is a good fit to help solve them. And if it is, I help start and lead delivery teams to make that happen. And that's what I do for my job. It's awesome. I love it. It's very rewarding. I also love recruiting people from these user group events. We just had Jim come to us, which is awesome.
And Jared too.
And Jared too. So anyone else want to start the trend? We can make this an, you know, a company user group.
I came here for the user group too.
Oh, there we go. That's good to hear. Just some hobbies. I'm big with my family. I got my new 1-year-old son right there. And but I love cycling. I'm huge into video games, playing a lot of Rocket League. I was playing Modern Warfare Warzone, but I got snagged back into PUBG, so that's happening. So, and it is what it is. And I do a lot of barbecue lately. So I'm living Traeger life, hashtag Traeger life, anyone? And been doing a lot of meat smoking, stuff like that. It's been great. It's a little more expensive now, so not as much these last weekends.
Praveen, did you have a question?
What's your smoking rig?
The Traeger.
The Traeger? Okay.
Yeah, it's great. You set and forget. I love it. We have a question already?
Maybe. Or maybe saying hi.
Okay.
Did you finally get saved?
You'll have to tell me because I'm not
Yeah,
seeing
no, he's got his hand raised, so I'm not
any Teams
quite
things
sure.
happening on my screen.
Otherwise, I'll put his hand down for him.
Yeah. So this talk's going to be an overview of intelligence and learning. I'm going to really just talk about AI and ML in a broad sense, and I'm going to bring it home into Java at the end of the day and really talk about how that ties into AI and ML can be a language global thing, not just Java, not just Python, of course, which is where a lot of action's happening. Because I'm going to show you the open sourceness and the open format, especially of Keras and TensorFlow and how models can be distributed to lots of computing environments. But before we get there, we're going to talk about what AI and ML is. And I hope everyone gets these two amazing American cultural references in front of you. We've got the awesome, Terminator and, Bender over there. So if anyone wants to take a stab at which one we think AI is, you can just point. But everyone likes to think that AI can be this big, scary, intelligent thing. And, maybe one day it can be. And
They both have teeth.
They both have teeth.
Whatever that.
And one of them's really strong, actually. But the reality of what AI is today is kind of more like Bender. It has a lot of strength, but there's not a lot going up there in the head, and it makes a lot of poor decision making sometimes. And that's where we're going to start with this. So machine learning. What is machine learning? Machine learning is using data to solve problems. And that's a little bit different than regular programming, which is solving problems with code, compiling them into binaries and running them. Instead, with machine learning, we're just using data. And what do I mean by that? Well, we're using data to train machine learning models. So in order to train a machine learning model, we have to have data, right? And that comes before the model, before even the code. Now, solving problems, we're solving those with the output of a machine learning algorithm, right? So once the model's been trained, it's done the learning, we can make predictions based on the data. Now, what's that really mean? Well, data can be anything. Data can be pictures, video, GPS, it can be text. It can even be, you know, pictures of a person understanding bone structures. There's all kinds of stuff data can be. And the problems that can be solved with that, you just have to use your imagination. Like if you could look at the world intelligently with historical knowledge, right? What could you solve, right? We have detecting cancer. We have self-driving cars based off of video. And we have traffic information for optimal routes. This is like 3 real life examples that are solved today in ML. They've actually been solved for over 10 years in ML, just companies weren't talking about it, but this has been done for a long time. Attributes of intelligence. There's learning, which is capturing and processing new information, reasoning, manipulating it, and understanding, which is actually creating new results of manipulation. Right. We have grasping truth, seeing relationships. These are all aspects of more human intelligence, right? And we have to ask ourselves when we create a machine learning model and make an AI system, well, what attributes of intelligence did we actually give our system when we made it? Because a lot of people like to believe that, or just, you know, don't know out of being naive or understanding the depth. They think that artificial intelligence is this form of general intelligence where it can just be smart in a myriad of different ways like a person can, but the reality is farther from the truth. We also have being able to consider the meaning of things, right? And separating facts from belief. So when we look at the types of intelligence, and these are coming from Gardner's theory of multiple intelligences, if you've ever looked into that. We're missing one of them, I think, but that's where this list comes from. So visual spatial intelligence, that's the ability to, visual spatial, you're perceiving, analyzing, and understanding visual information in the world around you, right? Picturing concepts, recognizing what things are, right? So this, the potential for AI right now, and a lot of my talks on AI are based off what we can do today. There's a lot of research that's always pushing the boundaries. But we can do image recognition. We can decipher videos, and then we can extract meaning from them. So we can detect objects. We can even detect some kind of intention sometimes, right? Now, bodily kinesthetic intelligence, that's the capacity to manipulate objects and use a variety of physical skills. And this is moderate to high. Now, I think everyone by now has seen the videos on YouTube of the people kicking the DARPA dogs. And we're all thinking, when's the dog going to bite back, right? When's it going to get violent? But, you know, those research firms have been using AI and a combination of what we call physical algorithms. Physical algorithms is a fancy way to say we wrote physics in a computer program. They use a combination of ML, AI, physics to create body kinesthetic movements. Oh, skipping ahead. Creative. There is not really any potential right now for AI to have creative intentions. And that is specifically the skill of creation, true invention, true discovery. Especially machine learning, which we just saw earlier, you have to start with data before you have machine learning. That's counter against creativeness, right? Creativeness is about being able to create something out of nothing, in a sense. Interpersonal intelligence, right? That's interpersonal is working with others, right? So being able to interact and effectively communicate with others, right? Verbal, nonverbal communication. Right now, we're seeing this with chatbots a little bit. Some chatbots are, way better than others. Some are amusing on purpose. One of the other guys in the office has written a very funny chatbot that makes mom jokes, and it takes out nouns and verbs out of people's Slack messages and will make good mom jokes. It's fantastic, and it's a little ML algorithm. Now, intrapersonal, as you can see, is none here. Intrapersonal is being able to be aware of your own emotional state. So hopefully there's no AI out there today aware of its own emotional state, because if that DARPA dog realizes it's angry for being kicked or beat with the broomstick, all the things they do in those funny videos, we're going to start having problems. Linguistic, right? The ability to understand and use spoken language. This is being done today. Actually, this is huge right now. I should probably change this to low to moderate. But we have apps right now that can translate in real time. And translating, as you may know, if you're into linguistics, isn't just about word to word. You have to translate meaning. And sometimes you have to translate idioms, right? And there's a lot of complexity to translation, actually. And then there's idioms that don't translate, and you don't want the meaning to be lost. Maybe that's where the low comes in, but I believe the field of linguistic ML is going crazy right now. And then we have the last one, and it's the only definite high one, logical mathematical. This is actually the foundation of ML algorithms, right? Recognizing patterns, logically thinking about problems, deciphering relationships, right? Being able to see what we can't see, even as humans, finding patterns in data. And sometimes it's not that humans can't see it, but there's too much data for us to see. So let's talk about AI versus ML. Now, these are terms that are sometimes used interchangeably. Sometimes people just say AI, ML, right? But they are distinctly different and they need each other, right? AI takes rules and data and it gives you answers. AI can make decisions, real decisions. Now, machine learning is taking data and answers and it's creating rules. Now, if you think about the order of things that we could actually create, AI versus ML, it's a little hard to create AI before you have ML, right? Because we absolutely have data about the world, right? But we don't necessarily have rules, right? How would you create a rule set for telling an algorithm how to recognize a cat in a picture? Could you make the rules? Maybe you try and write a bunch of if statement that says, hey, this is a tail if it's got a tail, 4 legs, and a head. Maybe it's a cat, but then you have to think, how would you even know that something's a tail and a bunch of pixels, right? So machine learning needs answers, right? And that's where the reasoning is done for the machine learning. Any of the intelligences is done for the machine learning because we have the data, and more importantly, we have the answers to the data. Right, so when you train a machine learning algorithm, you say, hey, here's the data, right? And then the answer I'm trying to solve, I'm going to give that to you too, right? And machine learning takes that sometimes millions of inputs, right, over millions of parameters. And every parameter is like an argument to the method, let's say, right? And it creates the rules. And oftentimes it creates the rules in a way we can't understand. Like it's some mysterious formula in RAM that is indescribable, right, in any way on paper, but it has created rules. And when you give it data later, it will run it past those rules and give you an answer. And that's when you have AI, is when you take the trained machine learning model and you actually use it to make decisions. And AI is usually not just one machine learning algorithm. It is a complex ecosystem of not just ML algorithms trained, but also other programming code and systems around it, other complexities, right? We talked about how they made a movable robot dog. It's a combination of physical algorithms and trained ML algorithms, right? An AI is usually a complex system of many parts, and ML is just one key component of that. Now, when we get into machine learning, I did kind of say something sort of right, sort of wrong, because I said we always have to have answers. That's not even necessarily true with machine learning, and we'll talk about why. What I was insinuating first, which is the machine learning most people know about, and that's the top right in the red there, supervised learning. Supervised learning is when you have the answers with the data. You already have it. So if you're training it with images, you give it the image and then you tell it what the image is, right? If you're trying to find emotional sentiment in tweets, you give it the tweet and you tell it the emotion the tweet's conveying.
Or commit logs.
Give it commit logs, you give it code and commit log, and you get the emotional state of the developer.
Exactly, yeah.
Right? You have to have the answer in supervised learning. It's like, teaching kids, like you show them and give them the answer and see if they can do it back to you or something. And then on the left, unsupervised learning here. That is when, just as it sounds, you don't have the answers. And two types of unsupervised learning are clustering and dimensionality reduction. Clustering is exactly what it sounds like. It takes a bunch of data. Let's say you have 1,000 rows, and you don't know if any of the data is related to each other, right? If any data point is related to any other. You run a clustering algorithm over it, it will separate the data into groups. Now, it necessarily won't tell you why, right? And that's when you have to do analysis on the clustering, and you determine with your human reasoning why it did that, right? But then if you like its reasoning, like you like the way it separated it, then that is a way to use a machine learning algorithm. And an example of unsupervised learning that's done all the time is in the finance industry, right? So oftentimes they will take in insurance and finance, they will take a bunch of unknown risks when doing a bunch of claim data, and they will apply clusters to it. Then when they get answers over time, they come back and do supervised, right? And so depending on what cycle you're in and like how much data you've collected is whether you may be doing supervised, unsupervised. Now, reinforcement learning is the interesting one. That is when, let's see, how do I explain it best? It's like supervised learning in the sense you map input and output, but the output you're mapping is not the right answer. The output you're mapping is like a hot or cold. Like, you know, you're getting closer to the answer, you're getting farther from the answer. So the algorithm will do something, and the best way maybe is to say it's playing a video game, like maybe something simple like chess. And reinforcement learning is a chess grandmaster may just teach the algorithm the rules at the chessboard so it doesn't break the rules. Or maybe you're trying to teach it how the rules work, right? It makes a move and you say good move or bad move, but you don't tell it why. You don't give it the answer on why it's good or bad. You just say good or bad. And you do that millions of times. And eventually reinforcement learning figures out the rules or whatever you're trying to teach it by just telling it, you know, hot or cold. So it's really interesting. You know, someone had a game play Pong, and that maybe not sound interesting, but he basically, like, every time the bar moved closer to where the ball was going to intercept, that's a good indication of reinforcement. Every time it moved away, bad indication. And it eventually figured out the physics of where the ball would always be and it would hit it. So those are types of machine learning. We're going to use our. Go ahead.
One thing you keep on saying is that we don't know why it does it.
Oh, we can know why in a few machine learning algorithms, but what's your question?
That's sort of it's a bit unnerving.
Yeah.
So it usually uses a neural network with a feedback loop where you're strengthening and weakening the interconnections between the simulated neurons.
Yep.
And that basically means that while we have a very large algorithm that will take an input and give you a deterministic output,
Yeah.
we're constantly tweaking the algorithm, and the algorithm is basically too hard to have anything like a back propagation where you explain why.
Yeah, and especially for reinforcement learning, which almost has to be a neural network, definitely. So one thing I didn't allude to maybe is, especially in supervised learning, if you're not using neural networks, you can use a regression machine learning algorithm. You actually can ask the algorithm what inputs matter most to the decision. That depends on the algorithm you use in machine learning though. So there is a way to figure out what features are important. So some algorithms, like a basic decision tree or a random forest decision tree, you can actually ask your trained model what is important to its decision and why for some of them. But that is more on the mathematical algorithms. The deep learning algorithms, we're still working on what's called explainable AI, which is becoming very important.
Yeah.
That I don't have explainable AI in my talk though.
Expert systems have like this huge ancient corner of AI, where before we even started using some of the more sophisticated mathematics, we were coming up with answers.
Definitely. Yeah, and like like a linear regression machine learning model, is simply doing the distance formula over every point of input you get. And we call it machine learning, but you can technically do that machine learning model by hand on paper. It would just take you a lot of paper.
Yeah, thank you.
Yeah, of course. Yeah, great question though. Thanks for bringing it up. So I want to talk about specific tasks that AI could potentially do, right? Why do we benefit from doing AI? Like, is AI going to put us out of business? Is it going to take away our jobs, right? Like that is often one of the biggest fears of AI.
Code is more concern for me
Yeah.
than AI.
And so,
Still.
yeah, so I want you to use your imagination a bit. What are some common elements of AI, right? Well, AI and ML, as we just discussed, is really good at performing a very specific task. If you think about it, ML, you have to train an algorithm with data. Well, that means that algorithm you trained is only good at one very specific thing, right? It's not good for anything else. And you have to make a model for everything. And then you have to consider if you use that model, it's only as good as the data you gave it. So if you give it completely new data that has no representation of the old data, its predictions are going to turn poor. But what that does for us is what used to be very analytical, like you have analysts in a room, is it can automate a very time-intensive analytical task, right? Like you're asked to say, hey, find out why all these customers are related, put them into groups. That's a clustering algorithm, right? Now ML can do it for you. So there's a lot of very specific things ML can do for us. Now, how do we benefit as programmers or even as a society from AI, right? Well, we get to use the Car Ride app to catch up on work. That's referring, of course, to a self-driving car using ML, right, and AI. Speedier, better diagnosis in general. When I read that, I think about like cancer detection. Right, nowadays, they send the X-ray to the ML machine, and the ML machine gives the doctor, not you, a bunch of predictions that speeds up their process of actually diagnosing you. It's not doing it for them, but it's giving them more information to make a faster, more informed decision, right? And it gives us time to focus on other tasks that are more creative, what AI can't do, right? So it's taking away time-consuming tasks, giving you, I guess, more time, a time you're in the zone. I'm going to kind of skip through some of these to get to my cooler slides. But it's like if you can describe a task, it's very repetitive. You can describe the outcome and the knowledge needed to perform the task. You could potentially, maybe, replace yourself with AI or that very specific task. Now, who's used a question on this? Who's used GitHub Copilot? No one in here's used Copilot yet? Come on, guys. All right, so Copilot, if you haven't used it yet, it is an AI ML system where they took all the code on GitHub, all of it, and they trained ML models over it. And they have like different models for languages, for frameworks. Like there's one for Java, then there's one for Spring, and it's all happening transparently to you in the background. You just have in Visual Studio Code a little plugin called Copilot installed, and you have to be in their alpha program. And if you type code, it will autocomplete it. And I'm not saying like IntelliSense, I'm saying it knows what you want to do. Because if you're doing anything like all the programmers before you, it's on GitHub, and it recognizes that pattern and will start auto-completing for us. So even for programmers, like we're not being replaced as programmers yet, but it's definitely going to speed up our autocomplete and our IntelliSense.
So again, we can focus on more creative.
More creative tasks, yeah.
Like Lombok on steroids.
All right, we're going to go over some of the language here. How am I on time? Okay, 7:30.
Doing great.
We're going to talk about neural networks a bit, and I have to talk about this. I want to make sure I got here because I'm going to show you a neural network. We have factors, we have outputs, right? Outputs are your predictions. right? Factors are the inputs that go into a prediction. It's easy to talk about stuff we know. So like, let's say you're applying for an insurance policy. Factors are going to be things like your age, your, maybe your gender, your sex, your, any of those kinds of properties, like have you been in an accident or not, what kind of car do you have? It's going to give it an output ultimately of your premium, right? And insurance companies with their actuaries have a combination of like hard set rules and ML algorithms doing this now. Weights. So weights are determining the importance of node outputs to another. So sometimes the algorithm decides its own weights after it gets a lot of data. Sometimes you give it hints on what you want it to weigh more, right? And you may have a reason why you want some parameters to weigh more than others, right? Biases, right? That's when you say, hey, you're trying to account for too much data in one input maybe. So you're trying to, adjust the bias for it so it doesn't weigh something too heavily. Like the algorithm may pick on a pattern that you intentionally don't want it to pick up on, you adjust the bias. Observations, these are the records used to test and train, right? So we have training data and testing data. The training data is what we run the model through with the answers. And the testing data, we have the answers too, but we don't give it to the model. Instead, we do the predictions and we observe how accurate those predictions are to the answers we have. That's how we get scores like accuracy in a model, right? So let's say you train on 70% of your data set, you withhold that last 30% to train. Now, back processing is after we've done all of that. We take what we've learned and we put it back into the input to make it more accurate. That's not maybe quite what happens, but that's the best way I can explain it. Complex. Go ahead.
Does the 70-30 split, does the 30% of testing data stay constant? Or is it again remixed with the 70% and then 30-70 split out again?
It depends on how big your data set is. If you've got a really big data set, then clearly the larger the data set that you're training on, you run into a problem called overfitting, where you basically can only recognize the data that you have. And so what you do is you always reserve a fraction of your data. And a lot of times that's quite a big fraction.
Yeah.
And what you do is you train a model and then you see if your model is a good representation for the rest of the data too. And so that way you sort of have kind of a control because you've split your data set into two phases and you can test it, build it on one set of data and then see whether or not it makes the correct kind of predictions on the others.
Yeah. And it also depends on like if you're trying to train 10 different models to test how they compare against each other, you generally want to use the same 70-30. And there's also other methodologies to do accuracy, like you have k-fold validation.
One left balance.
Yeah, you have a couple. The 70-30 split is the easy one to explain, but there's other techniques to take out further bias depending on how much data you have. But it's often one of the best splits if you have enough data. You may have to use some of the other methods if you have less.
Yeah, no. I was not asking about the 70-30% split as such. I was asking the 30% data that you held back for testing. After the feedback, do I mix it with the whole 70% and then pick out a random 30%, or do I hold on to that 30% for testing again?
It's about reinforcement learning using that for reinforcement, I think.
Or are you referring to maybe the back propagation? Is that what you're asking about?
I think that's about 30%. Is it the same 30%?
No.
Or is it?
The 30% is never given to the model as training, ever.
Yeah, it's to validate the model after
Yeah.
the model is trained. It's not to back propagate or to
Yeah.
have the model learn or anything.
Yeah, if you ever use your testing set and give it to the model while you're training it, you can no longer use it to test. Yeah,
Okay,
it has to stay pure.
Yeah.
Let's call it.
Based on it.
Yeah. You never want the training to see the 30.
Okay, got it. Thank you.
Yeah, and it even splits again sometimes. If you're tuning hyperparameters, then you'll do another split and have 3. It can get into things, but Cool. So layers, and this is a course we're still talking about neural networks. Layers is the grouping of the nodes. Your most outer layer, those are your input layers, and then we have layers in the middle. These are our hidden layers, and then the layers on the right, the output. We have inputs. We discussed those. Discussed the hidden layers, output. Hyperparameters. I kind of alluded to these. Every machine learning model has hyperparameters, which give it hints on how you want it to behave, is the best way to describe it. Even though we're talking about a neural network here, I'm gonna use the description of a decision tree. Or if you know what a binary tree looks like in general. One of the things you can do with binary trees or any tree is you can limit how deep they go, which means they maybe have to get wider, or you can limit how many individual leaf nodes are generated. Those are examples of hyperparameters. Right, so if you're using a decision tree machine learning model, you can actually give it a max depth. And the machine learning model has to figure out how to create a model with that limitation. Those are hyperparameters. Model structure, we talked about division of data. Cool. I should have replaced this with my Java slide. All right, I think that is what I wanted to cover. Let me go actually, so we have a little bit of time. Great. There's a process data scientists follow to do the model developments. We'll go over that real quick. So we talked about we need the data first. Prepare the data. There's so much in that step that it should be its own presentation. But often your data, and the reason I bring this up is, you know, if your boss asks you, hey, can we do machine learning on this data? The answer is almost always no, right? Right. There's actually so much work to get enterprise data ready for big time AI ML. There are things like you have to know your data is correct, first of all, which most organizations don't even know that, right? Then you have to make sure your data is clean and in a good format. A lot of machine learning algorithms, depending on what you're trying to do, don't do well with missing values, for example, right? Some of them do fine, some of them don't. And it really depends on what kind of model you want to train. Then beyond that, and when I said, is data correct? There's a lot of forms of correctness, right? There's like general, is the number accurate, right? But then there was their data mistyped? Then there's also, what is the business output of a model? Do we want to make sure we don't include sensitive parameters in there? Like, so a big thing about going on right now is diversity in AI. Like, do we want to make sure we exclude certain factors so they're not a decision in this right thing? That's all part of preparing the data. And there's a lot that goes into it. If you're doing a model, another weird thing about machine learning models, let's say you're doing a model to detect cancer. And, you know, I talked about scanning X-ray images. The problem with those kinds of models is like you only have a couple good examples to train the model, and then you have a million not cancer examples. There's actually things you have to do to the data and to the model to prepare it that, hey, I'm actually not giving you a lot of positive, outputs to learn from. I'm giving you like a million, not positive and 10 positive, right? And that's just because the sheer amount of data we have to train with. So sometimes you actually create almost dummy data, but it's not necessarily dummy because you make small variations of it to increase the amount of positive variations. There's so much that can go into that to ensuring that the model is going to be trained well, right? And it takes a good data scientist to understand these concerns and to do it. So there's some questions you can ask, if you ask someone, go, hey, let's do ML. Like, I heard we can download a model. And you can.
You also have to normalize for image data. You've got to basically normalize your images to where they have similar characteristics, so you don't wind up accidentally training a model that understands the high resolution images are generally what you're looking for, when in reality, no, you're looking for something else, and so on.
Yeah, and to your point, in most neural network images, they have to be trained with the width and height that they're going to be predicted with, and you can't deviate. And this is a funny one, the same RGB color space. People don't think about those little things, but it matters a lot when it's just a machine learning model, crunching numbers. You will test the model. You'll see the accurate. You'll update weights and biases. You'll record it, adjust the hyperparameters. There's even ways to adjust the hyperparameters in an automatic fashion until you get more accuracy. Of course, then you get into problems that were mentioned, like overfitting, and there's even underfitting, until we have the full life cycle, right? And we have a well-trained model. And then there's there's other problems, like you have what's not mentioned here, there's data drift. That's where actually the profile of your data just changes over time. And eventually it drifts so far that it looks very little like the original data it was trained on. You have to learn to recognize that and then retrain a model, right? Because again, models only know what you've taught them, right? Cool. I'm going to go ahead and stop here. I have so many slides in this, it's not even funny. But we are going to now look at some example in Java. Kotlin. Better Java, some would say. Let me go ahead and delete this folder. That's a good joke. All right, I'm gonna pull up my Gradle file here. You know what? I always forget to do this ahead of time, but I do want to make sure. Oh, I'm not actually showing on that screen. I'll change that for you just a second. But let me go ahead and get this. Wait, that didn't make any of that any bigger. Editor. There we go. JetBrains mono. Yeah, I'm getting there.
Okay, great.
Cool. That's a little bit better. All right, is my screen still sharing for you guys on the remote?
No, it's not showing on the remote.
We will reshare. Cool.
Yep, see it now.
All right, I'm using by JetBrains what's called Kotlin Deep Learning API. Let's go look at the documentation on this on GitHub, so I can talk about it before I show you the code. So this is, here it is, the GitHub. I could paste this link out and you can see it for yourself. This is a way to use a Keras distribution. Keras is kind of the higher level API to TensorFlow, so it's using TensorFlow 2 under the hood. And if you've heard of TensorFlow, which I hope you have, that's Google's version of their deep learning neural network. You've also got like PyTorch, which comes from Facebook, and a couple other things out there. This is just one I got working. So we're going to build our first neural network. And I'm going to kind of go over some of these lines with you. Feel free to ask questions. I may not know all the answers. But this is our machine learning model. So up here, I've imported, as you can see from this API, a bunch of these classes. So first we got sequential. That's the entry point class into a lot of Keras deep learning networks. This resembles Python, by the way, especially when it's written in Kotlin like this instead of in Java. You have the exact same terms as you would in Python. So if a Python developer, data scientist looked like this, it would look very familiar to them. Of course, they'd be like, why aren't you doing it in Python?
Why are there curly braces?
Why are there curly braces? Why do you have good autocomplete? That's always my joke, Python. So that's how we initiate a deep learning neural network. sequential. So the input 28, 28, 1. Well, that means I'm going to have 28 by 28 inputs. And the reason I have that is this neural network. Let's, oh, there was the link. This is taking this image data set of clothes. It's called the fashion, let me get the name, fashion MNIST. This is actually a very famous data set in the ML community. It's like a baseline data set to compare models against each other to test techniques. It's even built in to TensorFlow. Like I don't even have to download this image. It's like embedded. That's how like big some of these data sets are. There's a ton of these built into these AI libraries. They're meant to help you baseline and compare, right, different algorithms. So as you can see here, we've got some shirts, we've got pants, we've got long sleeve shirts, we have dresses here, shoes, sneakers, boots, purses. I'm not sure what's going on there. Someone made a cool visual.
Clustering of the.
Actually, you know that is a clustering algorithm. You're right.
It's cluster.
Cool. Good eye, Jim.
It's a good guess for
And this page goes into, why it was made, right? People love to this is going in, people love to use this to benchmark their algorithm. It's a very convenient data set, right? Another thing you'll notice is this data set's in black and white. So a lot of times when training neural network models for images, you make a decision. Does color add any benefit to the decision-making in an image? If the answer is no, you take it away, right? Color just gets in the way. If the answer is yes, you keep it. Because it actually adds a third dimension, like you go from n squared to n cubed of time and training, computation complexity, et cetera, right? And so that extra color space adds a lot of data. So that's what we're working with. Now these are 28 by 28 dimension pixels, right? 28 by 28, like we mentioned that in certain deep learning models, you have to know when you train how big the image is going to be, right? And you normalize that, right? You normalize the color space, everything about it. It's got to be the same. Some more advanced algorithms can sometimes deal with variation, not what I'm doing here. So flatten, this is going to take that and flatten it, take your 2D array and flatten it into a single array, right? Now we have dense. So when we talked about, we have our input layers, dense is our hidden layers. And what dense means every node is connected to every other node in this layer. And we have a dense node that starts out of 300 neurons. That means 300 neurons are going to take the flattened input to start the first level of decision making. Then I'm going to go to a second hidden layer, and I'm going to decrease the amount to 100 neurons. Now, what this means is some of the neurons are going to have what's called an activation function, which is what's called here the softmax loss, where it decides which neuron actually gets to send, a signal to the next layer. Because some neurons are better at knowing, oh, this is that or this is that, right? So you have to have enough neurons for the complexity of whatever you're trying to train it against. Now, if you want to know how to pick how many neurons you should start with, you're going to have to find a real data scientist and ask them. That is not what I am, right? I don't know if you know. But generally, you just start playing with numbers. I usually go by base of 2, right? So 64, 128, 250, and you just start going up until you realize you have diminishing returns. And I'm sure there's data out there on how much you pick. I'm not personally a data scientist. I'm kind of more in the ML engineering ops space, but you would have a data scientist kind of help pick this out, right? So we're going to go to 100 neurons down to 10. Now, the reason we go down to 10 is because we actually know there's only 10 outputs, right? And the outputs are here, as you can read them: t-shirt, trousers, pullover, dress, coat, sandals, shirt, sneakers, bag, and ankle boots, right? So those were the outputs we saw. So there can only be 10 neurons in the last layer. So you're telling this deep learning model, hey, start with 300 brain cells, no neurons, and you're going to have to decide, cut that down 2/3 to 100, right? And then down to 10. Now there's a lot of decision making on why data scientists would pick how many layers. There's also other layers I didn't even put in here called such as called dropout, right? Which is where you purposely drop even more data. Yeah, there it is, dropout, right? And so we can even see what happens if I add a dropout, but let's run it like this first. Going down, this is Kotlin syntax, if you're not familiar, but I have two variables I'm assigning here, train and test from fashion MNIST. We go look at that, that's returning a pair, right? But the IntelliSense here, which, you know, if you are a Python developer, you're really jealous at this moment in time. It's telling us what this is. This is a data set of 60,000 28 by 28 grayscale images of 10 fashion categories, right? It just told us everything we need to know. There's label descriptions, it's MIT license, there's all the stuff about it. So using the model we just defined, so this is the model definition, right? Now we're going to use it. First, we compile it. We're going to use the Atom optimizer. This is the optimizer you see the most. Again, data scientists will give you an answer on why you use this one. Everyone uses Atom though. I know that much. We're using the softmax loss function. I do know a little bit about this. You use softmax most often when you have multiple classifications. That is more than two. If you have a binary classification, there's probably a different algorithm we would use. Yeah, binary cross entropy, for example. And then there's a few reasons that, again, I wish I could enumerate with you on why you would pick others. But generally for multi-classification, you'll see people use softmax, right? Now, metric is interesting. We're telling the neural network that we want to go for accuracy. Now, you may think, don't you always want to go for accuracy? The answer is no. In fact, you almost never want to go for accuracy, but we are in this example. Showing you some of these other things, we have accuracy, MAA, MSE, MSLE, right? And there's even other ones here. These are just the simple ones. Now, the reason why accuracy is deceiving, and I'm going to go back to the cancer example. You're trying to diagnose cancer. You have 1 million images that you're going to test. Well, you know, let's say the rate of people getting cancer is only 1 or 2%. What does that mean?
Most accurate models just predict no cancer for all of them.
Is 98% accurate. But isn't that terrible?
Yeah.
So, yeah. So you could easily have a 98% accurate model and be very bad for your business. And that's where, you know, you really want to know the decisions you're making when you go, how do I tune the model, right? Because accuracy could be a terrible metric, depending on what you're doing with it. So now we're going to fit it to the data set, and you can see we're passing it the train. You don't see the word test here until we have evaluate, right? So training is happening, line 36, evaluate 38. We don't cross the two. I'm going to, if I remember right, I'm going to run it 10 times. And batch is how many inputs I run in a segment. These are hyperparameters. You would change these to adjust the behavior of the neural network training. We're going to get out of the metrics the accuracy, and we're going to print it. So let's go back to my main function, the comment out test here. Go and run. Where's my, usually it just pops itself up. Can you run? Oh, okay, it ran. Oh no, that was my last run. It's running again. Cool. So extracting 60,000 images of 28 by 28, and you can see it's pulling out, I guess, out of the cache there, but it's coming just from the jar file. And it's getting the 60,000 labels for each of those, right? And then it's getting 10,000, and this is where you can see there's your train and there's your test data. It's grabbing all that. And it is even output our labels, right? The input, flatten, dense, none, you know, and then your output. So we have an accuracy of 88%. Now, if we go look at the train code again, and 0.8888%. I hope that made sense. So we got that by evaluate against test, right? And print it out. Now, another cool part, which I wanted to get to in this talk, is save. So I'm saving this model to model/model1. So it made this model folder in my root directory here. And actually you can see some variable names. And then you open these files. Well, they're just a bunch of numbers. This document contains very long lines. This is the neural network compiled. This is a open format of Keras. There's a name for it. It's like MDF5, some weird name for it. The important thing is, yeah, you're not really going to be able to read this, but this model is portable. Anything that implements the Keras specification is going to read this model and use it. Now, the real power here is talking about the reality of, raise your hand if you think in the next year you're going to actually build a neural network in Java. Right? Anyone online? Right, probably not. But this is alluding to the greater reality of where data science is going, is it's not going to matter, right? It won't matter where you trained your model. Now, Python is so big in the ecosystem that it's going to be a while before you see data scientists truly operating in Java, right? Building and training models, because the ecosystem got so big in Python. And Python had so much early things that sped it along, like the creation of NumPy cannot be understated in making this whole, ecosystem possible. And then the creation of pandas on top of that, right? And then scikit-learn, the big, giant Python machine learning algorithm reference. And then, of course, Google made TensorFlow, which really revolutionized everything. Right? TensorFlow changed the world. So I'm going to comment out train here, and I actually have this other function called test. We can go and start running that. Let's go look at it. Test takes the labels. It's grabbing the data set again. But here I go, TensorFlow inference model, load, and I'm loading it, right? I'm telling it you have to kind of know stuff about the model, so I have to know the original shape. And I'm going to just call predict, right? And I'm going to make a prediction on index 0, it looks like. And if we look at the output here, the predicted label is 9, ankle boots, right? And actually, is that? Well, no, it's not in the order of this picture, unless maybe it's referring to the bottom right. Maybe it is in order. I don't know. But this is kind of showing you the greater possibility, which is that you can load a model in Java and run it. Now, the real power here is this could happen to you in the next year, because the data scientists are going to do their work and however they do it best, right? We're Java engineers, we don't care. But you could be approached one day and say, hey, in this, like, we want to run an experiment in this big enterprise application. We want to use a machine learning model. And instead of having to wire in a way to like load up Python and then communicate with Java, which of course there's plenty of ways to do that, you can just load it in Java. Just say, hey, point me to the S3 bucket, or whatever, send it to me in a zip file. I don't care. Give me the model. I'll load it right here using the same Keras library that Python used to train it. And you can do it native Java, right? Kafka, which is becoming one of the biggest data engineering platforms right out there right now, is a native Java implementation. Of course, you can do Kafka and lots of things, but it works best in Java. So now you're receiving tons of data in real time in your Kafka streams, right? In that consumer in Java, you can just load the model and ask for predictions, right?
It's actually doing that. They're doing that in the Children's Hospital in Atlanta, I think, and to actually look at intracranial pressure of newborns and infants, and they're using that to help save lives.
Wow.
Basically. Yeah,
it's done like the actual running of the predictions is in Java. Then,
yeah, right? I think that it may feed a Python model. I'm not sure, but we're able to get really fast turnaround for data through the use of Kafka. It's really mind blowing.
So this is the cool part is it doesn't matter how your data scientists made the model, right? If they made a deep learning model in Keras, you're going to be able to load it in native Java in the JVM with just one, extra item in your Gradle file, and you're going to be able to predict with it. And so I think this is the true power of where Java will absolutely come into the machine learning space is executing models and predicting models. Only time will really tell how much, machine learning engineers or data scientists do the training of models in Java, right? Right now, the Python ecosystem is kind of still winning out in there, but as you can see, we have the capabilities. I just loaded this model, which was created in Java and executed. And then you could take this model, zip it up, you can send it to Google Cloud or to Azure ML Suite or AWS, I'm sure they have one, and any of their built-in tools could then use this model too, because it is an industry standard format. Well, that's all I have for today's presentation. I hope I didn't run too late.
That was great.
Yeah.
I figured we could leave until 8:30.
Cool. Take questions.
So I posted the door prize chat and the door prize link in the chat. And for those of you who are here tonight, I'll make sure that you all get this link as well. A lot of great door prizes. We got door prize from JetBrains, IntelliJ Ultimate. We have Webicator training voucher. We have what else is it? Sonograph is from Hello Tomorrow. It's a cyclic dependency analysis tool. And Structure 101 IntelliJ plugin also does dependency analysis, or structure dependency cycle analysis. And those are the ones that come. Oh, Venkat Subramanian has donated a 1-year subscription to his Agile Learner website as well. Yeah, very, very generous.
1 year.
Yeah. So great resource and just all around great guy. So that's as far as door prizes go. Looking for speakers and presenters. Always looking for one next month. I'm going to see if I can get somebody from Redis to come and talk. But yes, always looking for presenters. And also market calendars. In middle of October, going to have. He goes by Han Solo, but his real name is Garrett Grunwald from Germany. He's going to come talk about a new feature in the OpenJDK called Crack. So basically it takes and will capture the state of your JVM warmed up, and it'll capture that some way when you start your JVM, it will start very quickly instead of having to perform warm-ups basically as it gets started. So everything will be kind of precompiled, and then everything is jitted out, and then takes a snapshot, and you can start your application without having to load everything up into memory. So say if you're running a Spring Boot application and it takes 30 seconds to start, well, then you can take and get that going a lot quicker now. So let's see. Dan Sline, you said there's some point there was a JSR for machine learning in Java as well. I don't know its stats. I think it's actually very close to being released as a visual learning API. I think something like that, but you could definitely use it for machine learning.
I actually think it's JSR 381.
Sounds okay. Yeah, that would sound right.
Hey, Dan.
Howdy, how's it going, buddy?
Great. Dan and I used to work together.
So I think that's about it. Anybody else have any other Java news that you'd like to share?
Udacity's doing like this thing where if you go onto like their website, or I don't know, I could probably share the link on Facebook later.
Sure, yeah.
Where they're trying to, I don't know, people are trying to look for work. They'll do like an intro course, and if you pass it, they'll do like the nano degree.
Okay.
And after that,
Nice.
you can get hired.
Oh, wow, good. Fantastic. All right. Anything else, anybody? All right. Oh, improving is hiring. A great place to work.
Oh, wow.
Yeah, oh, yeah.
Come work for us.
Yes. Great place to work. It's
We will
it's
take-
consistently voted one of the best places to work in Houston. And I just love it here. I'm gonna bring my friends along too.
Yeah. This is our space, by the way, if you haven't been here.
Yeah.
Cool.
All right. Thank you, everybody, for joining. And
Thank
we'll
you.
see
Thank you for doing this session.
All right.
Great talk.
Pleasure.
Great talk.
Thank
Yes.
you.
Thank you. Bye.
Stopping the recording.
Yeah.